Welcome to another deep dive. Today we're going to be tackling AI and machine learning. And
Oh,
judging by the stack of sources you've provided, exam questions, textbook excerpts, even some algorithm cheat sheets,
yeah.
you're not messing around.
Definitely not.
So our mission today is to decode this complex field and help you grasp those core AI and ML concepts that everyone seems to be talking about.
Yeah, it's such a fascinating area, constantly evolving.
Okay, so let's jump right in. And
Well, let's do it.
speaking of buzzworthy, we have to talk about generative AI.
Of
It
course.
feels like ChatGPT is dominating the headlines. But
hmm
our sources suggest it's just one piece of a much larger puzzle.
Absolutely. ChatGPT has certainly captured the public imagination.
It really has.
But it's crucial to remember that it's just one example of generative AI.
Okay.
What makes this category so exciting is its ability to create new content, new possibilities.
Okay, so it's not just chatbots then.
No.
What else falls under this generative AI umbrella?
We'll think about DAE generating images from text descriptions, almost like magic.
Oh, yeah.
Or Stable Diffusion, creating stunning AI art that's shaking up the creative world.
Yeah.
There's also Claude, another conversational AI, but built with a different approach than ChatGPT.
So we've got image generation, art, conversation. Where else is generative AI making waves?
Oh, it's just getting started.
Really?
We're seeing it compose music, build realistic video game environments, even design new protein structures for drug discovery.
Oh, wow.
It's truly pushing the boundaries of what we thought AI could do.
That's incredible, from art to science.
Yeah.
It seems like generative AI is transforming everything it touches.
It really is.
Now, shifting gears a bit, let's talk neural networks.
Okay.
Our sources mention these vanilla networks. What are those exactly?
All right.
In comparison to the deep networks we hear so much about.
Yeah, imagine a vanilla network as a neural network in its simplest form, an input layer, a couple of hidden layers for processing, and an output layer. It's a good starting point, but for complex tasks, you need more depth.
I see.
Hence, deep neural networks, or DNNs.
So DNNs just have more layers. What difference does that make?
It's all about learning power.
Oh.
DNNs, with their multiple hidden layers, can learn intricate patterns, hierarchical relationships, those subtle connections in data that simpler networks might miss.
Can you give me an example of where that extra depth is crucial?
Sure. Think about image recognition.
Okay.
To identify an object, a DNN needs to recognize features at various levels, from basic edges and textures to the overall shape and context of the object.
Yeah.
Those multiple layers allow it to build that sophisticated understanding.
So for those listening, understanding this difference between vanilla and
Yeah.
deep networks
Right.
is like having the key to unlocking the power of AI,
Absolutely.
especially in areas like image recognition and natural language processing.
A foundational concept.
Yeah.
Now, while we're on the subject of powerful techniques, our sources delve into ensemble methods. On the surface, it seems like combining multiple models should always yield better results.
Right. More is always better.
Right, but it's not that simple.
Wait, you're saying more models don't always equal better performance. Why not?
Well, ensemble methods, like the popular random forests, can definitely enhance accuracy and robustness, but there are potential pitfalls.
Okay.
One is overfitting. Imagine each model in the ensemble as an expert,
Yeah.
but they become hyper-focused on irrelevant details in the data, missing the bigger picture.
So it's like having a team that's too specialized. They know their little piece perfectly, but they can't see the overall strategy.
A perfect analogy.
Yeah.
Another challenge is computational cost.
Makes sense.
Training multiple models demands more time and resources, so it's a balancing act, potential benefits versus added complexity.
And I imagine there are times when adding more models just doesn't make a difference.
Exactly, especially if those models are making very similar predictions.
Okay.
You hit a point of diminishing returns.
So more isn't always better.
More isn't always better.
Okay, so ensemble methods.
Right.
Powerful, but proceed with caution.
Exactly.
That makes sense. Speaking of strategic approaches,
Yeah.
our sources also cover multi-class labeling.
Right.
I'm intrigued by this idea of using multiple binary classifiers to tackle complex problems.
Yeah.
Could you explain how that works?
Sure. It's a brilliant way to break down multi-class problems into smaller, more manageable pieces.
Okay.
Instead of one model trying to juggle multiple categories, you divide and conquer.
So instead of teaching a model to recognize cats, dogs, and birds all at once,
Right.
we simplify it.
Precisely. The sources highlight two common strategies, one visas all and one visas one.
Okay.
Imagine you're teaching a model to differentiate between those animals.
Okay.
With one visas all, you'd train separate classifiers for each. cat versus everything else, dog versus everything else, and so on.
So each classifier becomes a specialist in its assigned category.
Yeah.
That's interesting. What about the one versus one approach?
With 1 versus 1, you create a classifier for every possible pair. Cat versus dog, cat versus bird, and dog versus bird. When classifying a new instance, it becomes a tournament.
Okay.
Each classifier votes, and the category with the most votes wins.
It's like a democratic system for AI classification.
Exactly.
I'm starting to see how these multi-class strategies add a layer of sophistication.
Right.
Now, our sources also touch on Industry 4.0 and Industry 5.0.
Okay.
Those sound like futuristic concepts.
Yeah.
But I'm curious, what's the difference and why should we care?
Well, these terms represent different stages in the evolution of industrial automation.
Yeah.
Industry 4.0, which we're currently navigating,
Yeah.
is all about smart machines, the Internet of Things, and interconnected systems that can operate with minimal human intervention.
So like self-driving factory robots, automated supply chains.
Exactly, machines taking center stage.
So Industry 4.0 is all about machine autonomy.
Right.
But where do humans fit into this picture?
Yeah.
That's where Industry 5.0 comes in.
Exactly. Industry 5.0 recognizes that while automation is essential, human skills and ingenuity are still invaluable.
Okay.
It's not about replacing humans, but about collaboration, finding ways for humans and machines to work together more effectively.
So it's not a competition,
No.
but a partnership. Can you give me an example of what that collaboration might look like?
Sure, imagine AI-powered exoskeletons that help workers lift heavy objects safely.
Oh.
Preventing injuries, or AI systems analyzing complex data to support human decision-making in fields like medicine or engineering.
That's interesting.
It's about augmenting our capabilities, not erasing them.
That's a much more optimistic and human-centric vision.
It is.
Understanding this distinction is key for anyone wanting to stay ahead of the curve in this evolving landscape of work and technology.
Absolutely. It's about recognizing the potential of AI to empower us, not displace us.
Yeah, that makes a lot of sense.
Now, switching gears to another intriguing topic, our sources make it clear that sentiment analysis is all about
Emotions,
yes.
figuring out the feelings and opinions hidden within text. And they debunk a common myth. Sentiment analysis is not separate from natural language processing.
Right.
It's a core NLP task.
Right. That's right.
Okay.
Sentiment analysis relies heavily on NLP techniques. It's about using computational methods to understand the subjective information in text.
So is a movie review positive or negative?
Exactly.
How do people feel about a brand on social media?
That's it.
That makes sense. Could you break down some of those NLP techniques involved?
Yeah, sure. Think about tokenization, breaking down text into individual words or units,
Right.
and named entity recognition,
Okay.
which identifies and classifies key elements like people, places, and organizations. These are the building blocks that allow AI to grasp the nuances of human language, including how we express our emotions.
So if you're listening and you see a company analyzing customer feedback or tracking social media trends,
Yes.
you'll know that sentiment analysis, powered by NLP, is likely at play.
It is. It's a powerful tool with applications across many domains, from marketing and customer service to social sciences and even political analysis.
Wow.
It's about understanding not just what people are saying, but how they feel about it.
Okay, let's move on to principal component analysis, or PCA.
Okay.
It sounds complex, but our sources suggest it's actually all about simplification.
That's right. PCA is a dimensionality reduction technique.
Okay.
It's about representing complex data in a simpler, more manageable form without losing the most important information.
So it's like taking a massive multidimensional data set and squeezing it into a smaller space.
Exactly.
While retaining its most important features.
Precisely. Imagine you have a customer data set with hundreds of variables.
Okay.
PCA can help you reduce that down to a handful of key factors that explain 80% of their purchasing behavior.
Oh, wow.
That's the power of PCA, finding the essence of the data.
That's incredibly helpful. So it's not about making things more complex,
No.
but about simplifying them intelligently.
Exactly.
And I'm curious, where is PCA being used in the real world?
Oh, PCA is everywhere, from image compression and facial recognition to gene expression analysis and financial modeling.
Really?
Anywhere you have high-dimensional data, PCA can help you make sense of it.
Got it. So PCA is about finding the signal in the noise,
Yeah.
making complex data more manageable. Now let's talk about something that sounds pretty futuristic. Long short-term memory, or LSTM.
Okay.
Our sources confirm that LSTM is indeed
A type of node used in recurrent neural networks, or RNNs.
Okay.
LSTMs are specifically designed to tackle a challenge that standard RNNs often struggle with, remembering information over long sequences.
So it's like giving RNNs a memory upgrade. Why is that so important?
Well, standard RNNs can suffer from the vanishing gradient problem.
Okay.
Imagine trying to remember something that happened weeks ago, the details fade.
Right.
LSTMs help AI avoid that fading, allowing them to remember crucial information from much earlier stages in a data sequence.
Okay, so they help AI remember those long-ago details. That might be essential for understanding the bigger picture. Where is this type of memory power being used?
Well, this is a game changer for tasks involving sequential data.
Okay.
Think about speech recognition, text generation, time series forecasting, areas that are rapidly evolving thanks in part to LSTMs.
Oh, wow.
Take language translation apps, for example.
Yeah.
Their ability to accurately translate lengthy sentences relies heavily on LSTM's long-term memory capabilities.
It's amazing how seemingly small innovations can have such a significant impact.
It really is.
For our listener, understanding LSTMs is about grasping how AI is becoming increasingly capable of processing and understanding information in ways that mirror our own cognitive processes.
Yeah, it's a glimpse into the future of AI, where machines can analyze complex sequences, extract meaning, and generate creative output based on that understanding.
Wow. And speaking of understanding, let's explore Bayesian learning.
Okay.
Our sources indicate that it's based on a fairly straightforward principle. They mention that in Bayesian learning, the best hypothesis is the one with the highest probability of fitting the observed data, while also factoring in any prior knowledge.
Right.
So it's not just about finding any old pattern in the data, but about finding the pattern that's most likely to be true,
Exactly.
given what we already know.
It's like constantly updating your beliefs based on new evidence.
Okay.
Let's say you believe it will rain today.
Yeah.
That's your prior knowledge.
Okay.
Then you see dark clouds gathering, new evidence.
Yeah.
You update your belief to be more certain that rain is coming.
Yeah.
That's Bayesian learning in action.
So it's a more nuanced approach to machine learning.
It is.
Combining data with our existing understanding of the world, where is this being applied?
Think about spam filters, learning to identify junk mail based on the words used,
Oh, yeah.
but also incorporating your past labeling of emails as spam, not spam.
Okay.
It's also being used in medical diagnosis,
Oh, wow.
where doctors combine test results with a patient's medical history to make the most accurate diagnosis.
Okay. Bayesian learning, a powerful approach for navigating uncertainty and making smarter predictions. Now last, but certainly not least, we have support vector machines, or SVMs.
Right.
They have a slightly confusing name, but our sources clarify that.
Support vectors in SVM do not cross the decision boundary.
Okay.
That's a common misconception we should clear up right away.
Okay, then what are support vectors and what role do they play in SVM?
Imagine you're trying to separate two groups of people with a line.
Okay.
The support vectors are the people closest to that line, defining the boundary between the groups.
Okay.
SVMs aim to maximize the space or margin between the line and those closest individuals.
So it's like drawing a line, but making sure there's as much space as possible between the line
Yeah,
and the closest people from each group.
that's a great analogy. The wider the margin, the more confident we can be in the SVM's ability to classify new individuals correctly. This makes SVMs very effective at tasks like image classification, text categorization, and even bioinformatics. They're all about finding that optimal dividing line for accurate classification.
That's a powerful concept. Now, before we move on to our algorithm overview, I want to quickly recap some of the key takeaways from this first part of our deep dive. We started with generative AI. And wow, what a fascinating area. We learned that.
ChatGPT is just the tip of the iceberg.
Yeah.
There's a whole universe of generative AI models out there capable of creating everything from text and images to music and even protein structures.
It really is mind-blowing.
It's a field with incredible potential, constantly pushing the boundaries of what's possible.
Then we explored different types of neural networks, understanding that.
Deep neural networks, or DNNs, have multiple hidden layers that allow them to learn complex patterns and hierarchical relationships in data.
Yes.
Making them ideal for tasks like image recognition and natural language processing. That depth gives them the power to tackle those intricate problems.
We also delved into ensemble methods, where we discovered that.
Combining multiple models doesn't always guarantee better performance.
Right.
There are potential pitfalls like overfitting, computational costs, and diminishing returns to consider.
Right. It's about using them strategically,
Exactly.
not just throwing more models at a problem.
Right.
We then tackled multi-class labeling, learning that.
1v-sol and 1v-1 strategies are clever approaches for using multiple binary classifiers to solve problems involving more than two categories.
Yeah.
It's about breaking down complexity and empowering those classifiers to specialize.
We discussed the evolving landscape of industrial automation, distinguishing between
Industry 4.0, which focuses on smart machines and autonomous systems, and Industry 5.0, which emphasizes human-machine collaboration and AI augmentation of human capabilities. It's an exciting shift towards a more human-centric approach to automation.
we clarified the sentiment analysis.
Is a core NLP task that relies on techniques like tokenization and named entity recognition to understand emotions and opinions expressed in text. It's about unlocking the emotional layer of language and using that insight in powerful ways.
We demystified principal component analysis, or PCA, explaining that.
It's a dimensionality reduction technique that simplifies complex data while preserving essential information, making it easier to analyze and visualize. It's about finding the essence of the data, the key features that matter most.
We uncovered the power of long short-term memory, or LSTM, which
Is a type of node in recurrent neural networks that helps them remember information over long sequences, enabling breakthroughs in speech recognition, text generation, and time series forecasting. It's about giving AI the power of long-term memory, crucial for understanding complex sequential data.
we also explored Bayesian learning, a powerful approach that
Combines data-driven insights with prior knowledge to find the most probable explanations for observed phenomena. It's about updating our beliefs in a smart and systematic way, making more informed predictions.
And finally, we tackled support vector machines, or SVMs, emphasizing that.
Support vectors in SVM do not cross the decision boundary.
Right.
They define the margin that separates different classes of data, enabling effective classification. It's about finding the optimal dividing line, maximizing that margin for greater accuracy.
Whew, that was a lot of ground covered.
It was.
But I already feel more confident navigating the world of AI and ML.
Good.
And now that we've laid the foundation,
Yes.
I'm excited to dive into the specific algorithms mentioned in your source material.
Yes. Let's get into the nuts and bolts of these algorithms, how they work, and what they're being used for in the real world.
Stay tuned for part 2. Welcome back. I'm ready to get into the details of these algorithms that power the AI revolution.
Excellent. Let's start by revisiting the foundational learning types that our sources highlight: supervised, unsupervised, and reinforcement learning.
Okay, those are like the core learning styles of AI. Right?
Yeah.
I remember we touched on them briefly before, but I'd love to go deeper. So supervised learning is all about
Learning from labeled data. Think of it as having a teacher guiding the process. You give the model a set of inputs, along with the corresponding correct outputs or labels. The model's job is to figure out the relationship between them, so it can accurately predict outputs for new, unseen inputs.
So it's like learning by example. If I want a model to recognize different types of flowers, I show it tons of pictures labeled rose, tulip, sunflower, and so on. And it learns the distinct features of each.
That's exactly it. Predicting house prices based on features like size, location, and number of bedrooms is another classic example of supervised learning. You feed the model historical data with known prices, and it learns to estimate prices for new houses based on those features.
Okay, that makes sense. Now, unsupervised learning seems a bit more mysterious. There's no teacher, no labeled data. How does the model learn anything if it's just given a bunch of data without instructions?
That's what makes unsupervised learning so fascinating. The model has to be a detective, sifting through the data for patterns, structures, and relationships without any explicit guidance.
Can you give me an example of an unsupervised learning task?
Imagine you have a huge data set of customer purchasing behavior. An unsupervised learning algorithm could analyze this data and group customers into different segments based on their shared purchasing habits, even though you never told it what those segments should be. This is called clustering.
So it's discovering hidden structures in the data, like identifying different types of shoppers, without knowing their labels beforehand.
Precisely. Unsupervised learning is also great at anomaly detection, like finding those fraudulent credit card transactions that deviate from typical spending patterns.
Okay, I'm starting to see the power of unsupervised learning. It's like the AI is exploring and making sense of the world on its own.
Now, what about reinforcement learning? We talked about it being a bit more adventurous. How does that learning style work?
Imagine you're teaching a dog a new trick. You give it rewards when it does something right, and maybe a little scolding when it gets it wrong. Reinforcement learning works in a similar way.
So it's all about trial and error. The AI learns from its mistakes and successes. Exactly. In reinforcement learning, the AI interacts with an environment, takes actions, and receives rewards or penalties based on the outcome of those actions. Its goal is to learn a strategy or policy that maximizes its rewards over time.
Can you give me an example of where this type of learning is used?
Think about training a robot to navigate a complex maze. It starts by bumping into walls and taking wrong turns, but through trial and error and by receiving rewards for reaching certain checkpoints, it gradually learns the optimal path. This is how reinforcement learning is also used to teach AI to play games at superhuman levels.
Okay, now that we've reviewed the three main learning types, let's jump into some specific algorithms mentioned in our sources, starting with convolutional neural networks, or CNNs. They're all about images, right?
Right. CNNs are the superstars of image recognition. They're inspired by how our own visual cortex processes images, using layers of filters to detect patterns and features.
Our sources mentioned convolutional layers. Can you explain what those are?
Imagine sliding a small magnifying glass over an image. That magnifying glass is like a filter or kernel that scans for specific patterns like edges, corners, or textures. In a CNN, these convolutional layers extract features at different levels of abstraction, from simple shapes to more complex objects.
So it's like the network is learning to see by breaking down the image into its central part.
Exactly. And then there are pooling layers that simplify the information, focusing on the most important features. The output from these layers is fed into a fully connected network, like a regular neural network, which makes the final prediction, like identifying what's in the image.
It's amazing how CNNs mimic our own visual processing. Now, shifting gears to Bayesian classifiers, those are all about probabilities, right?
Yes, Bayesian classifiers use Bayes' theorem to calculate the probability of a data point belonging to a particular class. They rely on both the data at hand and any prior knowledge we have about the problem.
Our sources mention they're often used in spam detection. How does that work?
Think about it this way. If an email contains words like free, money, or miracle cure, the classifier would increase its probability of that email being spam, because those words are statistically more likely to appear in spam than in legitimate emails.
So it's like a detective building a case, weighing the evidence to make the most probable conclusion.
Precisely. Bayesian classifiers are also used in medical diagnosis, helping doctors assess the probability of a patient having a certain disease based on symptoms, test results, and their medical history.
Okay, probability, evidence, prediction. I'm getting the Bayesian picture. Now let's talk about linear regression. That one sounds more straightforward.
It is. Linear regression is a classic statistical method for predicting a continuous value based on one or more input features. The key assumption is that there's a linear relationship between the inputs and the output, meaning you can represent it with a straight line on a graph.
So like predicting house prices based on size and location, you find the line that best fits the relationship between those factors and the price.
Exactly. Once you have that line, you can plug in the features of a new house and estimate its price. Of course, in the real world, these relationships are rarely perfectly linear, but linear regression can still provide valuable insights and reasonably accurate predictions.
Got it. Linear regression, finding the line that tells the story of the data. Now let's move on to recurrent neural networks, or RNNs. Those are designed for a different kind of data, right?
Yes. RNNs are all about sequences, data with a temporal dimension like text, speech, or time series data. They have a unique feature, a memory of previous inputs.
So unlike other neural networks, RNNs can remember what they've seen before. Why is that so important for sequential data?
Think about predicting the next word in a sentence. The previous words provide crucial context. RNNs, with their loops that allow information to persist, excel at understanding this context. They're like the storytellers of the AI world.
I see. They remember the plot. Now, our sources also mentioned LSTMs and GRUs. Are those special types of RNNs?
They are. They're even better at handling long-term dependencies in sequences. Imagine trying to understand a novel where a crucial event from the first chapter impacts the climax. Standard RNNs might struggle to remember those early details, but LSTMs and GRUs excel at this.
So they have an even better memory for those long-ago details.
Exactly. And that's why they're powering innovations in language translation, speech recognition, and even music generation, where understanding the long-term structure of melodies is crucial.
Okay, fascinating. RNNs, sequences, memory, it's all clicking into place. Now, what about support vector machines, or SVMs? We touched on them earlier, but I'm still curious about how they work.
SVMs are all about finding the best boundary to separate different classes of data. Imagine drawing a line to separate two groups of dots on a piece of paper. SVMs aim to find the line that maximizes the distance between the line and the closest dots from each group. This distance is called the margin.
So it's not just about finding any dividing line, but the one that creates the most breathing room between the classes.
Precisely. The wider the margin, the more confident we can be in the classifier's ability to accurately classify new data points. This makes SVMs powerful for tasks like image classification, where you might need to differentiate between cats and dogs in pictures, or in bioinformatics, where you might classify different types of cells.
Okay, I'm getting a good visual of how SVMs work.
Mm-hmm.
Maximize that margin for optimal classification. Now let's move on to logistic regression. It's a bit confusing because it has regression in the name, but our sources emphasize that it's actually a classification algorithm.
You're right, the name can be a bit misleading. While linear regression predicts a continuous output, logistic regression is used for binary classification problems where you're trying to predict the probability of something belonging to one of two classes.
So instead of predicting a house price, it's predicting whether an email is spam or not spam.
Exactly. It uses a special function called the sigmoid function to transform the output into a probability between 0 and 1, representing the likelihood of belonging to a specific class. It's widely used in applications like disease diagnosis, where you might be predicting the probability of a patient having a particular condition based on their symptoms and test results.
Okay, probability predictions for classification. That makes sense. Now let's move on to decision trees. Those sound more intuitive, right?
They are. Decision trees are like flowcharts breaking down data based on features until you reach a prediction or classification. Each node in the tree represents a decision based on a certain feature, and each branch represents a possible outcome of that decision.
Our sources mention two types, classification trees and regression trees. What's the difference?
Classification trees are used when your target variable is categorical, like predicting whether a customer will churn or not. Regression trees are used when your target variable is continuous, like predicting house prices.
So the type of tree you use depends on what you're trying to predict.
Exactly, but the underlying principle is the same. Dividing the data into smaller and smaller subsets based on features until you reach a prediction.
Okay, it's like a choose-your-own-adventure for data. Now, how about k-means clustering? That one sounds a bit different.
It is. K-means clustering is an unsupervised learning algorithm used to group data points into clusters based on their similarity. Imagine you have a scatter plot of data points. K-means aims to find K clusters, where K is a number you specify, and group the data points so that those within a cluster are as similar to each other as possible and as different as possible from those in other clusters.
So if I wanted to segment my customers into 3 groups based on their purchasing behavior, I would use k-means with k equal to 3.
Precisely. The algorithm works by iteratively assigning data points to the nearest cluster center and then updating those centers based on the average location of the points assigned to them. It's like a game of musical chairs, where the chairs are the cluster centers and the data points are trying to find the closest chair.
That's a fun analogy. Where else is k-means being applied?
It's widely used in market segmentation, image compression, and anomaly detection. It's a powerful tool for uncovering hidden patterns in unlabeled data.
Okay, grouping data points, finding those clusters. Got it. Finally, let's talk about k-nearest neighbors, or KNN. It sounds like it has something to do with proximity, right?
It does. KNN is based on the idea that similar things are usually close to each other. Think about birds of a feather flocking together.
So it's like judging a book by its cover, or in this case, judging a data point by its neighbors.
In a way, yes. KNN doesn't build a model in the traditional sense. Instead, it remembers all the training data. When you need to classify a new data point, it simply looks at the k-nearest data points, its neighbors, and assigns it to the most common class among those neighbors.
So it's all about majority rules. If most of its neighbors are spam, then it's likely spam too.
That's the basic idea. KNN is a simple but often effective approach, especially when you have a lot of labeled data and the relationships between features and target variables are complex.
Okay, I'm really starting to see the diversity of these algorithms and how they each approach the challenge of learning from data in a unique way.
It's an exciting field.
It is. Now, before we wrap up this section and move on to broader implications, I think it would be helpful to recap the key takeaways from our algorithm overview. We started with convolutional neural networks, or CNNs, which are
the masters of image recognition using convolutional and pooling layers to learn hierarchical features from visual data.
Then we explored Bayesian classifiers, which are all about
Probability and prior knowledge. They use Bayes' theorem to calculate the likelihood of different outcomes, making predictions based on the available evidence.
We tackled linear regression, a classic statistical method for
Predicting continuous values based on the assumption of a linear relationship between inputs and outputs.
We delved into recurrent neural networks, or RNNs, which are uniquely designed to handle.
Sequences like text and speech, thanks to their ability to remember previous inputs and understand the context of sequential data.
We discussed support vector machines, or SVMs, which excel at
Finding the optimal decision boundary that separates different classes of data, maximizing the margin for greater accuracy.
We explored logistic regression, a classification algorithm.
Uses a sigmoid function to transform linear equations into probabilities, making it ideal for predicting the likelihood of belonging to a specific class.
We then moved on to decision trees, which break down
Data into smaller and smaller subsets based on features leading to a prediction or classification.
We talked about k-means clustering, an unsupervised learning algorithm for
Grouping similar data points together into k-clusters based on their proximity to cluster centers.
And finally, we explored k-nearest neighbors, or KNN, a simple but effective algorithm that
Classifies data points based on the majority vote of their nearest neighbors, leveraging the idea that similar data points tend to be close to each other.
Wow, we covered a lot of ground. It's amazing to see the diversity and ingenuity of these algorithms, each tackling the challenge of learning from data in its own way.
Absolutely, and this is just a glimpse into the world of AI and ML. There are many other fascinating algorithms out there constantly being developed and refined.
Okay, so we've laid the foundation, explored the algorithms. I'm ready to dive into the bigger picture. What does all of this mean for our world? And what should we be thinking about as AI becomes increasingly integrated into our lives?
Let's explore those questions in part 3.
Okay, we've explored the fundamental concepts and delved into the mechanics of various algorithms, but now I'm ready for the big picture. What does this AI revolution mean for us?
That's the question, isn't it? AI is no longer science fiction.
Right.
It's quietly woven into our everyday lives, influencing our experiences in ways we might not even realize.
You're right, I hadn't thought about it like that.
Consider those personalized recommendations you get on streaming platforms or the fraud detection systems that protect our financial transactions.
Yeah.
These are all powered by AI working behind the scenes to make our lives easier and more secure.
And it's not just about convenience.
Right.
Our sources highlighted how AI is transforming entire industries,
Absolutely.
from healthcare to transportation and finance.
AI-powered diagnostic tools are helping doctors detect diseases earlier and with greater accuracy, potentially saving countless lives.
Yeah.
Self-driving vehicles, still in development but rapidly advancing, promise to revolutionize transportation, making it safer and more efficient.
That's amazing.
And in finance, AI-driven algorithms are analyzing vast amounts of data, helping investors make smarter decisions.
It's incredible to think about the potential benefits, but I also can't help but wonder about the potential risks.
Of course.
As AI systems become more sophisticated, how do we ensure they are used responsibly?
That's a crucial question.
Yeah.
As AI evolves, we need to think carefully about issues of transparency and accountability.
Right.
Who is responsible when an AI system makes a decision that has a negative impact?
Yeah.
How do we ensure that these systems are fair and unbiased in their decision-making?
So it's not just about understanding how these algorithms work, but about considering their impact on society.
Exactly. We need to ensure that AI is developed and deployed in a way that benefits all of humanity, not just a select few.
Right.
This means having open discussions about the ethical implications of AI,
Yeah.
involving diverse voices in the conversation, and establishing guidelines to ensure responsible development and use.
You know, this deep dive has really opened my eyes to the complexity of this field.
It is complex.
It's not just about the technology itself, but about the human element. Our responsibility to shape the future of AI in a way that aligns with our values.
I couldn't agree more. AI has the potential to be an incredible force for good, but it's up to us to steer it in the right direction.
Well, this has been an incredible journey of learning.
It has.
I feel like I've gained a solid understanding of the core concepts of AI and machine learning, from the basics of neural networks to the nuances of specific algorithms. But more importantly, you've helped me appreciate the broader implications of this technology and the importance of engaging in thoughtful conversations about its future.
It's been a pleasure sharing this exploration with you.
Thank you so much for guiding me through this fascinating landscape.
You're very welcome.
And for those listening, remember, this is just the beginning. The field of AI is constantly evolving. Stay curious, stay informed, and keep asking those critical questions. The future of AI is in our hands. Thanks for joining us on this deep dive.